Hi, I'm Joel Siegel. I'm the lab director here for Liberty Oilfield Services. Today I'm going to talk about some specific tools that we use in our labs called viscometers or rheometers. We use these instruments to design our fluids and also to ensure that our frac fluids behave as designed. To understand what these tools do for us, let me back up and talk about rheology. Rheology is the branch of physics dealing with the flow behavior of liquids or dispersions. Fluid flow is all around us in the form of such things as water, oil, honey, shampoo, toothpaste, even wood and metals. When put into motion, molecules and particles are forced to slide along each other. This sliding causes friction, which is resistance to flow. Generally, the larger the individual components and the higher the concentration, the higher the internal friction and the higher the resistance to flow. The particles contributing to flow resistance can be caused by anything that makes up the fluid, from solvent or water molecules at nanoscale or 10 to the negative ninth meters to much larger particles such as minerals at the micron level or 10 to the negative 6 meters. Viscosity is also the measurement of this frictional resistance to flow by fluids. Viscometers and rheometers are the tool that are used to measure viscosity. Frac folks are very concerned with viscosity of their frac fluids. In fact, frac has a love-hate relationship with viscosity. We love it when our fluids gain viscosity because viscosity is part of what is used to transport sand as far as possible into formation. Once in place, the sand will artificially increase formation permeability and allow oil and gas to flow. Once the sand has been carried as deep into the rock as far as the viscosity can take it, however, we no longer want viscosity and we no longer love it. In fact, we hate it because once transport has ceased and the sand has deposited, the best thing for the frac fluid is to lose all of its viscosity so that the oil and gas can flow back to the well with lower resistance. So how do frac folks like to measure viscosity? First, I'd like to clear up some confusion over whether we use viscometers or rheometers. Both classes of instruments measure viscosity. The difference is technical. With the viscometer, the viscosity can only be determined via rotational tests. Rheometers, however, measure viscous properties under multiple flow conditions and can determine many more rheological parameters. At LOS, we actually use both viscometers and rheometers to fully describe frac fluids. In frac, we typically use fluids that are highly dependent on the flow conditions. So the viscosity of our fluids is more than one number. It's a curve that is dependent on the conditions that surround the fluid. For example, a fluid that has a viscosity of 1,000 centipoise under relatively static conditions at room temperature can have single-digit viscosity under high shear, high temperature conditions. The conditions frac fluids see are highly variable in terms of temperature and shear rate ranges. At Liberty, we like to quantify the viscous properties of our fluids along the entire flow path of that our fluids might encounter, from topside ambient conditions to in-pipe high shear conditions to downhole high temperature in-frac conditions. Traditionally, a rotating cup and bob viscometer, known as a cuvette viscometer, is used to make these viscosity measurements. API standard RP39 and ISO 13503 fully describe the current testing procedures used by the industry. There are many different manufacturers and options available for this type of instrument. Below, I have some images of various common cup and bob viscometers that we use either in our regional labs or in our on-location QC vans. These can all be configured using different bob, rotor, or spring combinations to match fluid type and provide more accurate readings. They can also be run at variable shear rates and temperature settings to better simulate well conditions. Some are limited to relatively low temperatures, and some can be pressurized to enable viscosity testing at higher temperatures. Because API, or the American Petroleum Industry, has defined this as a standard for the industry, these instruments have the same geometry and operate largely in the same way. These viscometers use a rotating cup and a stationary bob with a gap between the two that simulates the fracture. The outer cylinder or cup rotates to produce flow, and the deflection of the inner bob is measured as torque, which gets converted to viscosity. So they all measure torque with a defined shear rate. The rotational speed of the cup imparts a shear rate, and the bob measures the shear stress or drag force exerted on the walls of the cup and bob. The shear rate is the relative velocity between the stationary bob and the rotating cup divided by the separation gap. Interestingly, on all these viscometers, if you use the specific combination of an R1 rotor, B1 bob, and an F1 spring at 300 RPM, the torque reading will be exactly equivalent to viscosity and centipoise, which is why this is the most common setup and what folks in frac typically think of when they hear the word viscosity. More recently, some smart folks in the industry have come to the realization that frac fluids cannot be fully characterized using a simple viscometer. This revelation stems primarily from running many slot flow tests, which enable visualization of particle settling of frac fluids in a defined gap slot, which is meant to simulate flow in a fracture. It turns out that there isn't good correlation between the parameters that can be measured on a typical viscometer and the transport particles in these slot flow tests. Using a modern rheometer, aka fancy rheometer, however, allows you to measure many more viscosity parameters compared to an older viscometer. The hope is that one day, one or more of these new parameters will correlate directly with proppant transport. These rheometers are also far more sensitive at low levels of viscosity and shear rate, which enables more accurate measurements of the same parameters that are measured on viscometers. These rheometers can also be outfitted to be high temperature and high pressure, just like the viscometers. The biggest sacrifices are durability and cost relative to a simple viscometer. Although I would never rule it out, you're not likely to see one of these show up on your location. Rather, one day we'll be able to set a simple viscosity target that can be measured easily in the field, which has been correlated with the specific transport parameters which were measured on that fancy rheometer back at the district lab. One of the primary differences between those older viscometers and a modern rheometer is in its ability to quantify a fluid's elasticity. Defining a fluid's elasticity requires a highly sensitive instrument with the ability to take measurements while oscillating back and forth rather than in a single direction. Understanding whether your fluid is behaving elastically under your flow conditions will be one of the keys to understanding proppant transport. Below are some images of an oscillatory instrument used to measure elasticity in one of our district labs. In summary, in frac, we generally utilize two classes of instruments to measure the viscous properties of fluids. Those are cup and bob, cuvette viscometers, and modern rheometers. There is much common ground between them in that the modern rheometer can also measure everything that the older viscometer can measure. The modern rheometer, however, has much more flexibility in terms of geometries and measurement techniques that allow for measurement of many unique fluid parameters that will ultimately be used to correlate back to proppant transport. That's all I have for today. I'm Joel Siegel. For more information, please visit libertyfrac.com.